Right, so yeah, I'm Marcello, building Herodotus. I'm the CTO, so I'll try to not make it super technical, but be prepared. And first things first, Henry, thank you for your introduction. That was amazing. That has a lot of context. So maybe a few words first, what we actually do at Herodotus. So we do storage proofs, but we make them cool by adding snarks to them. So it's a nice combination, and with that combination, you can access whatever data from an L2, from another L2, L1 data on L2s, and most importantly, you can go crazy and read historical data at scale from smart contracts. So it is unlocking a lot of new application designs. And I want to briefly talk about it, but most importantly, how it's actually possible and how the tech works under the hood. Okay, so why historical data is cool? Actually, why data is cool. I was preparing the slides right before the presentation, so forgive me. So historical data. So first of all, like imagine that you want to access like a Uniswap v2 TWAP from a smart contract for a very weird pair of tokens, and you want to get that TWAP from 3 months ago over a time frame of like 2 weeks. Is it possible nowadays in a trustless manner? Well, no, for 2 reasons. First of all, that requires a lot of computation, and it requires data points, right? And the question is, how do we actually get the data trustlessly? Because on the EVM, and in general, any virtual machine running on the blockchain, you normally have access to what is currently in the state, which is kind of problematic, and you can't do it in an easy way. But with storage proofs, it becomes possible. Okay, so now another use case, so snapshot X. So maybe I should just give a quick introduction. What is the thing I like the most about snapshot X? Is that essentially you can vote on an L2 based on assets you hold on L1 without ever interacting with any bridge. And now how is it possible? Because, well, I can bridge my assets back to L2, but then it requires interacting with L1. So some users might be not willing to pay the price for that. So what is the other way? Well, I can send a message, but a message needs to be sent from L1 to L2. So we kind of have the same problem. So here we have a solution which is called storage proof. What if I can just prove as a user on some smart contract on L2 that I hold some assets on L1? And that's exactly what Snapshot X does with storage proofs. So yeah, that's cool. Yeah, so let's move on to the next slide. So let's ask the eternal question, what really a blockchain is and why it's a blockchain. So as you might know, it's a chain of blocks, but now most importantly, these blocks have something called block hashes. And what essentially a block hash is a hash of the entire block. And now each block contains the hash of the previous block. And that's exactly why we call it a chain, because by using cryptography, we enforce like a linkage. And this is an amazing property when it comes to dealing with storage proofs. So now, if I know some hash and I trust it, it means that I can prove that there is some block header that is actually valid. So if I know a valid block header and I know the previous block header, I can trustlessly prove it that this is the correct one only by knowing 32 bytes of data, which is the initial block hash, which is a pretty amazing property. Because again, by knowing some block hash X, I can literally iterate through the whole blockchain, like till the genesis block. So 16 millions of, more or less, almost 17 millions of blocks on Ethereum L1 as of today. So that's kind of cool, and this is exactly why historical data access is possible in a trustless way. Okay, so I mentioned block headers, so maybe a quick recap what a block header is. So I mentioned block hashes. A block hash is essentially you take this, you serialize it in a proper way, you hash it, and you get the block hash. And now what do we have? So parent hash, this is pretty important. I don't want to go and explain every single parameter in the header. So let's just focus on the 3 most important ones for storage proofs. So state root, transactions root, and receipt root. Okay, so I mentioned that a blockchain is like a linked list of headers. But now we also have something that we call a state. And a state is essentially like a database at the end of the day. And blockchains are very disorganized databases, where first you have this linked list, and then for each specific block you have a gigantic tree which represents a key value store. And this is exactly what the state root is. It's the root of this gigantic tree, which is also a cryptographic data structure. So you can do quite a lot of things with them. So to recap, we have state, we have transactions, because we can prove even the inclusion of some transaction, and we also have receipts. Okay, so I think that's pretty much it, what you should know on the high level. Okay, so this is like super basic, and how we can get advantage of it. So Henry mentioned that on ZK rollups, thanks to some properties of ZK snark and ZK snarks and ZK starks, you get cheap cold data and very cheap computation. So now let's remove the definition cold data and let's talk about bandwidth instead. So ZK proofs essentially give you unlimited bandwidth, almost unlimited bandwidth, and let's put it into braces. But you get very cheap bandwidth and very cheap computation. So why bandwidth? Why we really care about cold data or bandwidth in this case? So, if we want to access something from 2 months ago, it means that we need to iterate through every single block in the last 2 months. So that's a lot of computation, and most importantly, that's a lot of headers to pass. So that would be kind of crazy, to iterate through this list every single time someone wants to access some data. Maybe instead we can just literally create like a database that is easily accessible, and we can have some specific block handy and just literally take it. So that's exactly what we do at Herodotus, and we iterate through some blockchains constantly, and we created something that we call an accumulator. And what an accumulator is essentially a data structure, cryptographic data structure, where you can very easily pick up something. But again, you need to calculate it, right? And we do it thanks to ZK snarks. So yeah, very cheap bandwidth, again, because cold data is cheap, speaking of in the context of Starknet, and computation is cheap, well, because we use snarks, right? So I can do the computation once, prove it, and that's it. Okay, so I mentioned accumulators, and you might think that I'm talking about Merkle trees. That's like a natural solution to use for that specific case. So again, let's imagine that I want to access something from the chain, some specific block header, at some random position. And essentially the problem is that, again, I don't want to iterate through that. So the idea is, well, let's put it in the Merkle tree. But now I'm going to explain it why this is a terrible idea and how we do it differently. So Merkle trees, quick recap, is this idea that I get some data, I organize it, and then I hash the elements together, and I go upwards, and I end up with some root. Then I can create something that we call a Merkle proof to access whatever from this tree. Amazing. And by the way, as you see on my right side, there is like this image that shows the Merkle proof, so the blue blocks. So essentially, to get to the root, I just need to provide these elements. But this is very bad because the blockchain keeps growing, right? So we constantly get new blocks. So that said, with these new blocks, we need to reorganize them again and recalculate the tree. So we need to iterate through the blockchain again. So this just doesn't scale well. And also, we need every new block that is created, we need to add a little bit more of bandwidth to this computation. So Merkle trees are okay-ish, but they don't scale pretty well. And that's exactly why we use an accumulator called Merkle mountain ranges, where essentially, again, you can get a set of data set, commit it, but updates are very, very cheap because, the blockchain keeps growing, so we need to update the accumulator, right? And Merkle mountain ranges is essentially this idea that I have like an array of Merkle trees, but appends are very, very cheap. And the trade-off is that verifying the proofs, so proving that something is in the set, is a little bit more expensive. But that's okay. That's a good trade-off. So I don't really want to go into the details of how this works, but think of it as of an updatable Merkle tree. So yeah, we use this and they work pretty well. I highly recommend it if you want to use them in production. We have very nice libraries. Okay, cool. So we have a little bit of background. So what I discussed so far has nothing to do with storage proofs. I was only talking about like proving the chain, so building like a oracle for block hashes. So a few facts. maybe before I get to the facts, as you might imagine, iterating through millions of blocks for each chain, or let's say that you want to access some data from Polygon, so this number is even bigger, and you're still doing the same computation, this might be, well, challenging, at least, to do everything in one single proof. So, as you know, generating big proofs requires a lot of computation power, so you need a pretty beefy machine. And at some point, your computation may be so heavy that there is no such a beefy machine on AWS. So how we actually do this, we can use recursion, but recursion is a nice approach, but it's not perfect. Why? Because we cannot parallelize. But on the other hand, we can also have an approach that uses recursion, but is parallelizable. So, by the way, if you feel that I'm going too much into technicalities, just raise your hand. If not, I will explain how this actually works. Okay, no hands raised. So, recursion. I can start from some block hash and just iterate, let's say, through the first 1,000 blocks. I generate a proof, then I redo the same work again and verify the second proof. And I generate one, then generate another, and I keep combining them, and so on and so on. So this is the approach on the right side. But, well, this might take a long time, right? Because I need to do everything sequentially. So what if we just make it in a bit smarter way? So the smarter way is to get the blockchain, chunk it into pieces, process each piece independently, and then just kind of build like a tree of proofs. And that's literally what we do and we use. So this combination essentially allows you to have a proper block hash oracle in a very nice way, efficient way. Okay, cool. So now let's get to the storage proofs. So yeah, this is how a storage proof looks like. So I mentioned at the beginning that having cheap bandwidth and cheap computation is pretty important when it comes to dealing with storage proofs. So I was explaining that in the context of actually building the accumulator that gives you access to whatever block hash. But now that we're getting to storage proofs, we actually need to also verify the storage proof. Quick recap. A storage proof is, well, let me just jump back to this slide. So we have a state root, and this is the root of the state tree. And this is something that we call a Merkle-Patricia tree. I don't really want to go into the details of how they work, but think of it as just a fancy Merkle tree. Great. And now this Merkle proof for this type of trees looks more or less like this. That's pretty huge. And that's pretty painful when we want to verify it on the EVM or something. But again, on Starknet we have cheap code data, so it's not actually a problem. But when it comes to verifying the stuff on the EVM, obviously we want to use snarks and we actually do it. So the cost goes down significantly. I'm talking about code data, not necessarily computation. Okay, so let's move to the next one. So I mentioned snarkification of the proof. So as Henry mentioned, verifying proofs is also computation, right? And we can prove computation. So we can verify the storage proof inside the snark, and then we don't need to provide the whole storage proof, which is gigantic, or even we want to go crazy and calculate a Uniswap v2 TWAP, which is a lot of storage proofs, and also a lot of proofs to the Merkle mountain range, because we want to pick some specific blocks. That's a lot of stuff, right? So what if we just put all of that inside the snark? And now we have something pretty succinct that just proves us, hey, this is the actual output. So this is why you want to use them, and we use them for that specific reason. Okay, so I very quickly mentioned, like I said, the order is not really great. But again, the state tree on Ethereum is essentially like a Merkle tree, Merkle-Patricia tree. So it's essentially like a hexarray Merkle tree. It's just a fancy one. And the thing is that computation, to verify this proof, computation-wise, it's a bit cheaper, but you're paying in bandwidth. So that's exactly why snarks are even better when it comes to this type of trees. Okay, so now combining these things together with these accumulators and the ability to verify storage proofs against some hash that you don't need to trust because someone has proven that this is correct by just iterating through the chain, you can end up something like this. You get the Ethereum state tree, you generate the proof, you pass this proof to Starknet. Starknet just verify that, hey, that this state root is correct, and how it's happened, well, you just verify a Merkle mountain range proof. And voila, you can access some L1 data from Starknet, or like Optimism, or whatever. So that's kind of cool already. And you can pass data at scale without the necessity of sending messages back and forth. Okay, so let's break it down into pieces, how this whole system works. So first of all, we need to get access to some trusted block hash, and we call it like getting the commitment. Then we need to access something specific. So we need to iterate through the chain, build the accumulator, or just save the block hash, the block header, and finally we verify the storage proofs. So now I'm gonna just iterate through some of the approaches, because there are many ways you can actually do the same thingy, and depending on your resources available, you might pick different ones. So first thing, let's talk about how you actually get the commitment. So I wrote down 3 approaches. Obviously there is more of them, but I just want to quickly discuss these 3. So approach number 1, messaging. So messaging, what does it mean? We just call a contract on Ethereum that is going to send some block hash, which we get using a specific opcode. So if we trust the EVM, we should be pretty much confident that this block hash is correct. Amazing. So we can send it to some L2, and then from this block hash we can do this whole crazy computation. But by the way, emojis are pretty bad when you convert to PDF. So this one is a sad emoji, and it says that latency-wise, this approach is not the best, right? Because essentially the latency of our system is the latency of generating the proofs plus the latency of the message incoming. Gas cost, well, it's pretty expensive because we need to send a message from L1, so we are paying L1 gas. So that's expensive. When it comes to trust, well, we literally don't need to trust anyone, so that's okay. And do we have some computation overhead? Well, not really, because we just send a message at the end of the day. Second approach, consensus verification. So why consensus verification is actually cool, and I'm even mentioning it, because at the end of the day, the consensus is about agreeing between all of the nodes what is the latest block hash. So that's it. So, and this is also computation. So what if we can just prove this computation, or like verify all these attestations inside some smart contract? So latency, we have a little bit of latency because, like I said, we might very likely want to prove this computation, because that's, again, many attestations, many signatures to verify. So doing that inside the smart contract is probably not the best idea, unless you are a Starknet. Gas cost, well, we need to verify a proof, a pretty big one, so that's also going to cost us a little bit. Trust, we don't need to trust anyone, right? Because we just literally act like a light client. Off-chain computation, well, very likely we want to prove this computation, so we need to generate the proof. Oh, by the way, these emojis are very, very bad, because I have like sad and happy, and it should be very happy, happy, not happy, sad, super sad. So, okay. So this is about consensus validation. Another approach is essentially building our own attestation committee. But again, in many types of applications, you don't want to use this approach because it's the cheapest, it's the fastest, but you're sacrificing a little bit on trustlessness. So latency, you have no latency because you just need to generate like a signature that attests something, and the attesters can be, for example, all the applications that don't really require that much security. They just come together and say, hey, I'm gonna put my signature, you put your signature, and you get 60 guys, and the 60 guys will just, over an MPC protocol, will end up with one signature, which is pretty fast normally, depending on the signature scheme. So gas cost, we are very happy because we just verify signature at the end of the day. Latency, again, we're using an MPC protocol. MPC, generally speaking, is, I don't remember the name of the property, but it's parallelizable, more or less. So it doesn't take that much time. Off-chain computation overhead, you don't really do computation. It's mostly about like, very fast networking between the participants of this computation. But again, we are sacrificing a lot of trust. Okay, so this is the part number 1 of dealing with storage proofs, getting the commitment, aka the block hash, and finally block hash oracle. So the naive approach is, well, while we iterate through the blockchain, let's just save every single block header. So gas-wise, that's madness, because it requires a lot of bandwidth and a lot of storage. And 60 millions of blocks, where every block header is roughly 1 kilobyte of data, it's gonna be gigs of data with a big G that we need to store on the actual chain. And storing anything, even on L2, is actually not cheap. So you definitely don't want to do that. But you don't need to prove, because you just use the resources from the L2, L1, whatever that is. It's going to cost you a lot of in terms of gas, and that's a lot of storage. Okay, on-chain compression. On-chain compression is essentially building this Merkle mountain range or any other type of accumulator, and we call it on-chain compression. But we can do it on-chain. So the computation actually might happen, for example, on Starknet. So prover overhead. Sorry, PDFs are very bad for emojis. We are like okay-ish, because still this operation should be done ideally on L2 like a ZK rollup, so we still need a prover. Gas cost, I mean, it costs a little bit, but we are not using storage, so we're very happy, so the gas cost is not that bad. And off-chain compression is doing literally the same, but not on an L2, but you just spin off your own prover and you do it. And you can even parallelize it, right? So there is a lot of overhead, but again, it's very cheap and you use literally no storage. So we are happy. Okay, last part, verifying storage proofs. So when it comes to proving this computation directly, oh, by the way, let me first go through these approaches. So standard proof verification, we just get a proof. We take this proof, we show it to a smart contract, and the smart contract tells us if this proof is valid or not. So we don't need a prover, so there is no overhead. Latency, well, we just need to query the RPC node that returns a proof, and we are happy. Verification costs, we are extremely unhappy because it just costs a lot. Second approach, we can just snarkify this verification, or the verification of multiple proofs. Sorry, this is the third approach, actually. So we need to prove this computation. There is a bit of latency because we need to generate the proof. And verification costs, we should be, generally speaking, happy. Because when it comes to verifying proofs still on EVM, the biggest cost is normally cold data. So on places like Starknet, it's cheaper, right? So the verification is relatively cheap. And another approach, let's just verify multiple proofs inside one ZK snark, or let's just aggregate the snarks, whatever. The outcome is more or less the same. So prover overhead, yes, significant because we need to do it. Latency, yes, because we need to prove more stuff. But verification costs, we are very happy because we just batch things together. Okay, so I think that's pretty much about that's all about my presentation. And by the way, these things sound crazy, but if you want to actually use storage proofs, just reach out to me. As Herodotus, we have very nice APIs for that, which do this all crazy optimizations under the hood. And yeah, I don't know, questions?
I have one comment and two questions.
Yep.
So the comment is, you told that there is no such solution that can provide the storage proof, and it's actually funny that you made the example of Uniswap, because exactly Uniswap, they have a smart contract.
But for V3?
For, if I'm not mistaken, they stored the prices in pairs in that smart contract, and they used exactly the Merkle tree. So I used the smart contract, and it works until now. So there is such some kind of solution, but of course, your thing is much more proficient.
I mean, I think that the TOOP is available, but for V3, not for V2.
It is available.
For V2?
For V2, you need a separate contract that gets pinged every 8 hours or so.
Oh, yeah, but yes. But you still need to interact with a contract, and you need to literally have a keeper that does it. So.
Yeah. Okay. So the first question is, I didn't quite understand how you can extract. Can you extract any slot of storage from any piece, from any smart contract? And how is this possible?
So essentially, depending on what is the language you use, you have some, for Solidity, you have a specific storage layout. So essentially, Ethereum, like the database, the tree itself, is just a database, a key value store, where the key is some hexarray number and the value is also some hex. So essentially, if in Solidity you have a variable and you call it, like for example, A, you just assign it like something that we call a slot index. Like for example, 1, if it's a mapping, then you need to concatenate things together, you hash it all together. And this hash is essentially the key that points to some value. And yeah, that's essentially it. Whatever you write to a smart contract can be accessed. And the funny thing about storage proofs is that you not only can access state, but even like receipts. So you can prove that some event was emitted, for example.
Okay, thank you. And the second question?
Mm-hmm.
You mentioned the API for that,
Yep.
but it doesn't make really a lot of sense. I would rather would have a smart contract that I can call on chain to prove that some storage was real, because that's.
But you need a prover.
Yeah, I need proof on chain. That's the thing. Like, I can prove it myself off
Mm-hmm.
chain.
Actually, the API that I mentioned, we actually generate this proof for you. We do all the aggregation, we choose like the best option, and then this proof ends up on the chain and gets verified by the on-chain verifier.
But will it be possible to do from the smart contract?
Yeah, I mean, you can also trigger the API for a smart contract by just emitting the event. We catch it, we generate the proof. You can actually generate the proof on your own, also verify it on your own.
Okay, thank you.
But like again, you need a very beefy machine, a lot of infra, and also the best thing about our API is that the more people use it, the more proofs you can aggregate, so it gets cheaper for anyone to use it. It's actually way more convenient for you to use the API rather than doing it on your own.
But sometimes it's really important to use it on chain. You know, for example,
But you can use it on chain.
if you build an oracle for Uniswap and you need some historical data from a few blocks behind, for example, then you really need it on chain, because like off chain it's not so useful. You know, I can off chain.
But these proofs are actually verified on chain.
But okay, what do you mean by API? Is it like a smart contract endpoint or backend endpoint?
Both.
Okay.
It's just a way how you actually trigger it.